very unlike. Anyway, it's equivalent, the totally probability. So there is only one way to get 180, and there is only one way to get 30, right? Because you have to get all of them equal to 6. But if you go to the center of the bell, right? Center of this bell-shaped histogram that you try to get, the reason those configurations are highly probable is that there are many, many ways in which you can obtain that number if you throw your dice, right? So it's essentially the number of possibilities. The probability to get one of those configurations is always the same. But the number of configurations that give you that result is actually very large. And that's why your distribution gets this funny bell-shaped feature. Okay? It's just a number of configurations. Now, this is something that is.
If we say normal, this normal distribution. This implies that since what always occurs is at the mean each time, so does that mean that the average is much is the normal?
No. It means normal distribution. Actually, I don't know where the name normal comes from. So let's call it Gaussian distribution because Gauss invented it. I don't know where the name normal distribution comes from. I know that it's frequently called this way, but it doesn't mean that you should take this distribution as to be the average or whatever to be normal in the sense that it's. I think it most probably comes from the fact that it frequently occurs because of central limit theorem in physics and mathematics, and therefore it's more or less the rule. And all the others are exceptions, but it's the rule for sums of independently distributed random variables, right? So that's the point. Anyway, so I promised that I would explain in simple terms what is entropy, right? Entropy is a name that was introduced in the context of thermodynamics to describe essentially reversible, irreversible processes in thermodynamics. The name itself means in Greek, I just checked it, inside transformation. So it's something that refers to changes of state or of a thermodynamic state. But nowadays, the most, I would say, useful well, it's much to get there. You need that pen? So nowadays, the simplest possible introduction to the concept of entropy is actually information theory. So forget about the story and the way you learn entropy in your previous courses. Let me ask you the following question. So you know what is this? This thing here. It's a traffic light, right? So red means if you see red, what do? You stop. If you see green, what do? You go. And if you see yellow, well, either if you can, you go as fast as you can, or otherwise you stop if you cannot pass the intersection, right? Now, the reason you give a meaning to these three colors is that when you pass through a traffic light, if you drive, for example, in Trieste, sometimes you see yellow, sometimes you see green, sometimes you see red, and therefore you know what to do, right? And in practice, well, we could imagine, for example, that the probability of having red is equal to 2/5. I don't know how much it is in reality, but seeing yellow is equal to 1/5. And the probability of seeing green is 2/5. And you go through Trieste, sometimes you see yellow, sometimes you see green, sometimes you see red, and you know precisely what information you get from these three colors. But now imagine that you drive in Trieste at 2 a.m. overnight, right? So what happens to traffic lights overnight? I don't know in your countries, but did you ever see what happens in Italy? Traffic lights overnight. They're all yellow blinking, right? So you see only the yellow color. Well, let's do yellow. And the probability of yellow is equal to 1. The probability of red is equal to 0. And the probability of green is equal to 0, right? So what information now you get from this yellow?
You're studying that it will always be yellow.
You don't get any information. And that's a useless color. It could be turned off as well. And there's nothing, it doesn't tell you anything, right?
Yeah.
There's no information associated to that color. It just means the traffic light is off, right? So that tells you something that is intuitive. I mean, this example of the traffic light during the day and overnight tells you something useful. If you have an event in probability theory that is certain, it doesn't carry any information. Let me make another example. Suppose that you go to a room and there is a guy who's talking and you're able to hear just a few words, right? So sometimes you enter and you say pasta, sometimes bread, sometimes tomato. You know what he's talking about because you know he's talking about food, probably he's discussing some recipe. It gives you some information, right? And that's because you know, it could have said something else. So you had a certain probability to get different words of different, or you had a certain finite probability of getting different events. But if this guy would be repeating his name, you know, for me, Alessandro, 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 like this, always the same word every time you enter, what information do you get? Nothing. Nothing. So you see, information is connected to the probability of a certain event occur in your probability distribution. And if an event is certain, then you don't have any information associated to it. So in this question of defining what information means is a question that those who developed information theory ask themselves, you know, back in the last century. And according to this example, you come up with the idea that information, the function information associated to an event that is certain should be equal to 0, right? So if something occurs with probability 1, it doesn't give you any information. And in addition, information is something that is positive or equal to 0, right? It's a function that characterizes how much knowledge or whatever you can get from a certain event that occurs randomly. In addition to this, you want another rule to be satisfied by your function that characterizes information. You wanted the probability of a pair of events, which is IPN times Pn, according to probability theory, should be equal to the sum of informations, right? IPN plus IPN. So, for example, if I have two traffic lights in a row, and I see green, green, it means I can, you know, it's the same as you can pass in the first, you can pass in the second. So the amount of information that you get in the pair of events is the same as the sum of the two individual ones. Now, what function has these three properties of being additive? So having this property here, this one, and this one, the logarithm, right? So in practice, this constrains our choice for the information function. Since Pn is smaller or equal to 1 for a discrete distribution, it tells you that the information function should have this form, Pn. Okay, should be a logarithm with a minus sign in front because Pn is smaller than 1, right? And therefore, and I has to be positive, right? So this is essentially what we have to get. This has to be our information. Now, there are different choices that you can make in principle. Now, in standard information theory, people choose B equal to 2 and A equal to 1. So the log is in base 2 and the coefficient is equal to 1. So this is information. And in particular, if I have an event like throwing a coin, right, in which I have probability of having head and tails equal to 1/2, you see that the information associated to pH is equal to the information associated to PT, which is equal to 1, right? Because it's log is minus log base 2 of 1/2, which is equal to 1. Now, this tells you that this is, in these units, this is 1 bit of information. Right? You know, bits, I mean, this thing that is being used in computer science. So this is 1 bit of information. In statistical mechanics, we will see that we will be using as B the Euler number, and A is going to be equal to our Boltzmann constant. And that will give us the entropy, right? So these are two faces of the same coin. Actually, if you follow the course, I think Matteo Marsiglio is sitting here in another section. He's giving a class on statistical mechanics, which is, you know, fully starting from information theory. So he's building all statistical mechanics on the basis of information theory. All right. So this said, we know what is information. We know how to, given a discrete distribution, how to associate information of a certain event given the probability that this event occurs. And now the question we have is, what is the entropy? Well, the entropy, so let me write it. What is entropy? The entropy of a distribution is the average information content. That's it. So this means that S is the average over the distribution of R, Pn, right? So this is by definition sum over n belonging to our set of events C, Pn, IPn. Now you see that according to the definition, this is minus A sum over n Pn log of Pn. So this is the entropy in information. Okay? So, for example, suppose that, so let's select the rules of information theory. So B is equal to 2 and A is equal to 1. If you have a dice, right? You throw dice. What is the entropy associated to the probability distribution for a dice throw?
1.
No, no.
1, 6. So the log of logging is 2 of 1, 6 is
just log of 6, correct. So S is log of 6. Log in base 2 of 6, which is, I hope it's correct, 2.58 something. So that's the entropy associated to drawing a dice. Yes.
In the entropy formula, so you need to write B also.
B here?
Oh,
Yes, I forgot. You're right. Okay, so now, why is the entropy important? Yeah, you heard this story that entropy always grows and the entropy of the universe grows all the time until we reach a completely, the thermal death of the universe, in which everything is completely disordered. So very pessimistic, right? Very pessimistic. Anyway, so why a state of maximum entropy is frequently associated, at least conceptually, to a state of maximum disorder? Okay? Well, let's think about it from the point of view of information theory. If you have, so this is a statement, if you have n which belongs to a set C, which has a number of elements in C equal to n, then we can ask ourselves, what is the probability distribution that has maximum entropy? What is the probability distribution defined on this set that has the largest entropy? What it means to have the largest entropy, it means to have the largest information content. So what is the probability distribution that has the largest entropy? Can we imagine?
Yeah, 1 over n.
1 over n, exactly. Everybody is equally probable, and they're all equal to 1 over n. So the probability, the most disordered probability distribution, the one in which essentially the variables have exactly the same probability to be observed, is the one that maximizes the entropy. Now, you can easily prove it for two variables. So if the probability of head is equal to 1/2 minus delta, and probability of tails is equal to 1/2 plus delta, then the entropy is going to be equal to minus 1/2 minus delta log of minus 1/2 minus delta minus 1/2 plus delta log of 1/2 plus delta. And now, well, if you expand from small delta, you will see that this is approximately log 2 minus 6 delta squared. So you see that for delta equal to 0, you have a nice maximum. And then for finite deltas, the entropy decreases, right? So the entropy. All right. So, and yeah, so what did I want to say? Yeah, so well, I don't remember what I wanted to say, so let's go on. Let's move on. Anyway, the maximum, the entropy is maximized. Sorry?
I want to ask the delta. Why you make the delta?
Well, I'm asking myself whether the entropy is maximal or equally probable. So therefore, I have to make the distributions slightly asymmetric. So it's not exactly equally probable, but they have to act as a subtract because it has to sum up to 1, right? So I put a delta, and then I compute the entropy for small delta, and I see what is the deviation from the maximum at delta equals 0. And I see that delta equals 0 is a maximum. Okay? And then I have deviations from this maximum given by this rule. All right, so now, yeah, so what I wanted to say is that, well, so this is actually, in practice, you could, if you would be able to measure the entropy, you could be able to see if your friend is cheating you. Well, right. So because it's an information, the deviations from the maximum value are an information about the symmetry of the distribution, the probability distribution. Now, the entropy has also another important property, which is that it's additive. So sum of Pn and n is equal to Spn plus Spn, right? So it's an additive function for two lengths. It's very easy to prove it. So let's do it. So S of Pn and then is equal to S of Pn times Pn is equal to minus sum over n and then Pn log of Pn. And now, well, you write up this log as a sum of two logs. Pn log Pn plus log of Pm. And then, well, so since sum over, so let me write it here, sum over n Pn and sum over n Pn is equal to 1, right? You see that in this formula, look at the first one. So you see that in this formula, in the first component, you can perform the sum over Pn, you will get 1, and then you will have remaining will be the sum over n. So you will have minus Pm log of Pn minus sum over n Pm log of Pn. And this is the sum of the two entropies, Sn plus Sn. Okay? Is it clear? Yes?
So why do you write the sum over Pn and Pn?
Well, because it's true.
Oh, yeah, I know.
So I'm saying, yeah, I know that you know it's true. So I'm saying, here, look here. I first perform the summation over n. And since sum over n Pm is equal to 1, because Pm is normalized, what remains is only the sum over n Pn log of Pn, which is this first term. And I do the same with the second. So the fact that these distributions are normalized means that I can perform one of the sums, and the other one that remains will give me the entropy. You see?
So you basically cannot skip them.
Yeah. So let me just sum over one. Okay. So the fact that the entropy is additive is exactly what makes the entropy for the thermodynamic entropy an extensive function, right? Because as I explained yesterday, if you, for example, ask yourself, so imagine you're throwing many coins, right? Or throwing many coins, imagine that you can throw a coin, you can throw a spin. because a spin is an object that has two configurations. So if you want to build your own easy model or your own model for spins, so take many coins and put them in a row. And this is the equivalent to conceptually to a spin chain in a sense. So now, if you put your spins in a row, then you ask yourself, what is the entropy of the entire system? If they are all independent and there are no correlations, or only short-range correlations, is the entropy of the space plus 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 the entropy of the space. You see? So the extensivity property of the entropy in statistical mechanics and thermodynamics is connected to this particular property that I wrote down, to this sum rule for the entropy. Great. So now it's time to do one little exercise together. So instead of going straight to thermodynamics, let us try to apply these ideas of statistics to the simplest possible problem of dynamics you can think of, which is the random walk. Have you ever heard this name? Random walk. Okay, you're experts, so I'm sure that this exercise will be random. This random exercise will be done by everybody quickly. All right, so a random walk is defined as follows. Well, you can do it in more than one dimension, but let us be straightforward. So let us think about a lattice in one dimension. And from each lattice point, from each side, we have a probability Q to go to the left and a probability P to go to the right. And then P plus Q is equal to 1, right? We have two possibilities. So in other words, we can represent this as the probability of performing a step sigma, right, at a certain time. And this is P times delta sigma plus 1. So you have an increment plus 1 with probability P, and you have an increment minus 1 with probability Q. Okay, so this is our discrete probability distribution for a single event. And now I want to ask myself, what is my position after n steps? So this is my question. What is my position after n steps? Well, in order to know what is my position after n steps, I have to compute the variable x, which is the sum over j from 1 to n sigma j. And now I'm going to ask you the following question. Suppose that we perform a number n sufficiently large of steps. Okay, so n is much larger than 1. And now I want to know what is the probability distribution of big X. What is the probability distribution with which of my displacement after a number n much larger than 1 of steps? What is P of X? Can someone give me an answer? What is P of X going to be? After many, what is P of X? How is P of X going to look like?
This is going to be the different number of states, and decide about the probability of having a certain number of states on the right and a certain number of states on.
That's correct. That's absolutely correct. However, my question is, so, and we will get there. So, but my question is much simpler than this. I just want to know, on the basis of basic principles of life, how is P of X going to look like? What? I didn't get it. That's
multiply P power N.
That is correct, but my question is much simpler than that. We will get to the P to the binomial distribution. You're right. But my question is, on the basic of what I told you and what you learned, what your grandmother told you, etc., and basic principles, how is P of X going to look like for a large N? It's going to be a Gaussian. Why? Okay, well, yeah, a bit more than this. Why? Because X is not independent. Is not politically independent. Why? Let's be precise. Because X is the sum of independently distributed random variables. Okay, you have to, in physics, you have to be, unlike in politics, you have to be very precise, okay, when you answer a question. So it's a Gaussian because X is a sum of independently distributed random variables, and for large N, I can use the what? I can use the
Gaussian.
no, I can use why it is a Gaussian because of the central limit theorem. Okay, you know, if central limit theorem is the justification of any Gaussian. Okay, so whenever you say it's a Gaussian, well, it's a central limit theorem, right? What else can it be? Whenever something is a sum of independently distributed random variables, then because of the central limit theorem, the limiting distribution is a Gaussian. That's it. Since it's a Gaussian, it's characterized by what? By mean and variance. And therefore, you see something very powerful. When you were telling me if I want to compute the, when you were telling me the distribution is P Q to the N, P to the power 1 minus N, etc., etc. We will introduce the binomial distribution in a second for this process. But in principle, you tend to think immediately, okay, I compute a distribution, I see how it looks like, etc., etc. But the central limit theorem allows you to do something very, very important. I don't want to know precisely what this distribution how this distribution looks like for small n. I don't care. If I want it for large n, I just compute two quantities, the average and the variance, and I know what is the distribution. That's it. Okay? You see the way of thinking, it's important. Okay, so what is the average? Average of this.
Average of
So, well, the previous years, I was, when I was asking this kind of questions that require some calculation, well, this is the simple one. And the price was an ice cream. But this year, I don't know with COVID whether I can hand out ice creams. So anyway, without a price, what is the average of X? Can you calculate it quickly?
Yeah. Average of X would be average of size of G.
Is the average of sigma, and
It should be from here, P plus Q.
no, not P plus Q. No.
Yeah, and P minus Q.
P minus Q?
Yeah, and multiplied by P minus Q.
Okay, so these are identically distributed. So this sum is n times the average of sigma, right?
Yes.
And this is equal to n times the average of sigma, which is P minus Q, right? Because you have P times 1 plus Q times 1 is 1. So you get P minus Q. Which tells you something important. You have equal probability to go to the left and to the right. You go nowhere in average. You stay there, right? In average, you don't move. Okay, which is what happens to a drunk person.
You don't get the P minus Q.
You don't get the P minus Q? So let's do it slowly. This is n. So probability of being 1 times P, sorry, times 1, plus probability of having minus 1 times minus 1, right? Because these are the two possibilities. Now, the probability of having 1 is P. And the probability of having minus 1 is Q, but it's multiplied by minus 1, and therefore we have minus Q. So this is our average. Now, what is now the variance? In order to compute the variance, we need to compute x squared minus average of x squared, right? Good. So we have to compute x squared. So this is equal to the sum over I and j and sigma I, sigma j, right? To find some other ways, cutting my ears. Okay. So now this sum has two possibilities. One are the terms in which I is equal to j, right? So it's sum over I from 1 to n, sigma I squared. And then all the terms in which I is not equal to j, from 1 to n, sigma I, sigma j. Now, sigma I squared is equal to 1, right? Because you can go to the left or to the right. And the step is 1 or minus 1. So therefore, this is equal to n. What? Why p plus q? Well, not multiplied by p plus q, you're right, but p plus q is equal to 1. And therefore, also p plus q is gone. Plus sum over I not equal to j n sigma I, sigma j. Now, I and j, if I is not equal to j, are uncorrelated variables. Okay? Uncorrelated. And therefore, the average of the product is equal to, if two variables are uncorrelated, the average of the product is equal to? No. No.
We can just do when they are all the same and then remove when they are not the same. Subtract.
I already did that. You see, I already took, and sigma I is equal to sigma j squared. So I already took the terms in which I is equal to j, but here sigma I and j are different. So these are two variables that are different variables and they are uncorrelated. Now the average of uncorrelated variables is what? No. It's much simpler. So if I take sigma I and sigma j, they are uncorrelated. This average is equal to? So let's do it. Look. is equal to the sum over all configurations of sigma I plus and minus 1, P of sigma I, then the sum over all configurations of sigma j equal to plus and minus 1, P sigma j, sigma I times sigma j, right? They are correlated, so one is distributed one way, the other is distributed some other way. Yeah, you see that this is equal to sum over sigma I, P sigma I times sum over sigma j, P sigma j, right? In other words, is equal to the average of sigma I times the average of sigma j. If two variables are uncorrelated, the average of the product is equal to the product of the averages. Okay, so keep this in mind. We will see it many, many times in this course. Okay, so let's put this in a, I don't know, in some frame. And now use it here. And if we use it, then we have n times plus sum over I not equal to j, n, then we have sigma I times sigma j. But the average of sigma I and the average of sigma j are the same, right? Both of them are equal to P minus Q, correct?
Yes. Yeah.
And therefore I get n plus sum over I not equal to j, n P minus Q squared.
Yeah.
Okay, so now how many terms are in this sum? I'm summing over all i's not equal. Both I and j are varying between 1 and n, but I and j are to be different. So how many terms I have in this sum? 2? N squared minus n. Because if I did not have the constraint having I not equal to j, I have n squared terms. But I'm removing all the ones in which I have I equal to j, which are n. So it's n squared minus n. So therefore, this is equal to n plus n squared minus n p minus q squared. Okay? And therefore, if I now take average of sigma squared minus average of x squared, what do I get? I get n plus n squared minus n p minus q squared minus n squared p minus q squared, right? And therefore I get that this is equal to 4 times n p times q. Because it's n times 1 minus p minus q squared. Is it correct? Let's do it slowly. So it's n times 1 minus p minus q squared. So this is n times 1 minus p squared minus q squared plus 2pq. No, actually, it's not. Yeah, so that's it. That's what it is, right?
Yes.
What I wrote down before was incorrect. Many apologies. That should be correct. What? But actually, just a second. P plus Q squared is equal to 1. And now P plus Q squared is P squared plus Q squared plus 2PQ. And this is equal to 1. Therefore, I can write this as N times P squared plus Q squared plus 2QP minus P squared minus Q squared plus 2QP. And therefore, what I wrote was correct. P plus Q. Okay, it's correct. You see that it's correct? Okay, now, so two important things in this result. You remember last time that we said that in the central limit theorem, if you compute the, I always make a mess between confuse standard deviation and variance. The standard deviation is x squared minus x squared, and the variance is the square root. Okay, good. That's my confusion. I mean, I'm not able to keep these two terms distinguished in my mind. So anyway, the variance, which is the square root of x squared minus x squared, you see that it goes like, it's going to go like square root of n times the square root of 4pq, right? But it's going to scale like square root of n in such a way that if I take the variance divided by the average, I'm using the same letter. Too bad. Sigma for that. So let's write it like this: delta x squared square root. So you see that if I take the ratio of delta x squared square root to the average of x, this will go like 1 over square root of n, which is exactly what we expect from the central limit theorem, right? In addition, since I computed these two functions, I can immediately write down for n much larger than 1, okay, what is p of x? And p of x, I know that in this limit is going to look like a Gaussian. In particular, it's going to be 1 over square root of 8 pi n qp times exponential of minus x minus n p minus q squared divided by 8 times n qp. So this is going to be the limit of the for large n of my probability distribution of x. By the way, do you know in which process you get a probability distribution of displacement that looks like a Gaussian and increases linearly in the number of steps that you perform? Which physical process? How is it called, the physical process in which the variance of the displacement grows linearly in time? That's correct. It's called diffusion. Okay? So this is, if you have never seen it, this is actually the first example, a discretized version of what happens in diffusion according, for example, to the diffusion equation that you probably have already seen. Okay? The continuum limit of the random walk is the diffusion equation. Okay? All right. So now this is what we got just on the basis of just the central limit here. So what I've done up to now is I just said to myself, well, I know that this is the sum of independently distributed random variables. Therefore, I know that it satisfies the central limit theorem. Therefore, I know that I can calculate the limiting probability distribution by just computing the average and the variance. And that's it. It's going to be a Gaussian. Now I could take a different point of view and ask myself, okay, so is this really correct, what I've done? And in order to answer this question, if you don't believe, it's correct, right? It has to be correct, and otherwise the theorem is wrong. But if you want to check for this process how the Gaussian comes out from the exact solution, you have to first find the exact solution. So I'm sure that you've already seen this, but let me redo it for you. Sorry. So if x is equal to sum over j from 1 to n sigma j, then clearly displacement can be computed in terms of, as your colleague, I don't remember your name, I apologize, but before said, so you can perform n steps, nr steps to the right, and left steps to the left. Then, in the presence of this pair of numbers, which are characterized by having a sum which is equal to n, then x is equal to their difference. Right? And now I can ask myself, okay, given n events, how many ways do I have to partition them into nr steps to the left and nl steps to the right? Well, this is given by the binomial factor, right? So the number of ways is actually equal to n factorial divided by n right factorial times n left factorial. Okay? Therefore, the probability distribution to observe a certain x is equal to n factorial divided by n right factorial and left factorial times the probability to find r movements to the left and nr movements to the left, to the right, and left to the left, which is equal to p to the power nr. P is the probability to move to the right, q to the power n left. All right. Okay, so now notice one thing that is important, that n right can be written as x plus n divided by 2, and n left can be written as n minus x divided by 2, right? Straightforward to see this. Now, given these two things, then we can rewrite our formula as n factorial divided by n plus x divided by 2 factorial, n minus x divided by 2 factorial, p to the power n plus x divided by 2, q to the power n minus x divided by 2. Okay? Now, I want to see how this function looks like in the limit in which n is very large. Well, this is the exact solution. There's nothing to discuss. But now I want to check whether this exact solution becomes a Gaussian in the limit in which n is very large. So now I'm going to show you how to do this using well, essentially an expansion. You first take the limit of large n, and then you take the limit of small deviations from the average. So let's first take the limit of large n. In order to do so, let me take the log of this probability distribution, En equals. This is equal to, if I take the log of this expression, is going to be equal to log of n factorial minus log of n plus x over 2 factorial minus log of n minus x over 2 factorial plus n plus x over 2 log of p plus n minus x over 2 log of q. Now, I assume that n is very large, and x is not too big, is not comparable to n, which means that both this number, and this number are very large. I assume them to be very large. Now, if they are very large, then I can use what? Stirling formula, right? You see that everybody knows Stirling formula. Log of n factorial is n log n minus n for n very large, right? And therefore, I can rewrite this object here as approximately using the Stirling formula n log n minus n minus n plus x over 2 log of n plus x over 2 plus n plus x over 2 minus n minus x over 2 log of n minus x over 2 plus n minus x over 2. Now you see that this term, this term, and this term cancel out. Okay? And therefore, this comes out to be equal to n log n minus n plus x over 2 log of, no, I'm missing something here. I didn't write it. Well, plus the other terms, right? Plus the other two terms. So this is this times the log of n plus x divided by 2 plus log of p, right? Minus n minus x divided by 2 log of n minus x divided by 2 plus log of q. Now something interesting comes out. You see that this n here, I can rewrite it. Oh, let me do it in green. I can rewrite it as n plus x divided by 2 plus n minus x divided by 2. If I do so, I can just put this term together with these two ones, right? And the n here will come to divide the argument, because I will have log of n plus x divided by 2 minus log of n. So we'll divide these arguments. See? Therefore, I get that this is equal to minus n plus x divided by 2 times log of n plus x divided by 2n plus log of p plus minus n minus x divided by 2 times log of n minus x divided by 2n plus log of q. Great, so now, since I divide by n, let me introduce the following variable, little x, which is big X divided by n. So if I introduce this variable, let me write it in green here. Introduce this variable. Now you see that I have minus n times 1 plus little x divided by 2 times the log of 1 plus little x divided by 2 times p, right? Because I combined the two logs, minus n times 1 minus little x divided by 2 log of 1 minus x divided by 2 times 2. Correct? You agree with me? Okay, so this probability distribution, therefore, I can rewrite this as minus n times f of x, where f of x is the combination of these two logs. Okay? Now, this means that, remember that this was the expression for the log of Pn, and therefore Pn itself is equal to a constant times exponential of minus n times f of x, where f of x is this object here. It's 1 plus x divided by 2 log of 1 plus x divided by 2 times p plus 1 minus x divided by 2 log of 1 minus x divided by 2 times q. Now, whenever you have a function that is e to the minus n times some function of x, right? And n is large, n tends to infinity. Well, so this function is essentially exponentially. So if f of x has a minimum, right? F of x is done this way, looks like this. So the function exponential of minus n f of x is going to look like this. So this is f of x. Well, let me do it properly in the next one. So if f of x looks like this, so f of x is something like this. So it has a minimum. This is f of x. Then the function exponential of minus f of x is going to have a maximum where the function f of x has a minimum, right? So it's going to be maximum here. And then it's going to exponentially go to 0. I mean, I'm not able to draw it. So go to 0 very fast away from this maximum, right? And therefore, if I want to approximate to figure out where the most of the probability distribution is concentrated and get a good approximation for this, is just enough to find what is the minimum of f of x and expand close to this minimum, right? So what is the minimum? Minimum of f of x? Well, I just take a derivative. So f prime of x is equal to 1/2 log of q over p 1 plus x divided by 1 minus x. And this should be equal to 0, which means that 1 plus x should be equal to, divided by 1 minus x should be equal to p over q. Or in other words, that x should be equal to p minus q. Right? No. So this is the maximum. And it's not surprising because, by the way, this is the average, right, of x. And now, how do I expand close to the maximum? Well, f of x close to this maximum is going to look like f of x bar. And by the way, f of x bar, if you substitute this, is equal to 0. So this is equal to 0. Plus f double prime at x bar divided by 2 times x minus x bar squared. Right? And now, what is f double prime of x? Well, if you calculate it just by taking a derivative of what I wrote down above, you will find that f double prime of x is equal to 1 over 1 minus x squared. And if you substitute p and q, this is 1 over 4 times p times q. And therefore, what do we discover? That our f of x is equal to our f of x is equal to that this is equal to x minus x bar, which is p minus q squared, times 1 over 4 times pq times 1/2. So this is x minus p minus q squared divided by 8 times pq. Okay? This is the expansion of my f of x. Sorry? Why is it equal to 0?
We just have the f first derivative equals 0, but we don't have the f.
Let's check it. So if we don't, well, I didn't show it, I just told you. So f at is equal to 1 plus P minus Q divided by 2 log of 1 plus P minus Q divided by 2 times P plus 1 minus P plus Q divided by 2 log of 1 plus Q minus P divided by 2 times Q. All right, so now, actually it's not equal to 0, you're right. It cannot be equal to 0, otherwise I don't get the normalization correct. You're absolutely right. So then now 1 is equal to P plus Q, and therefore this is equal to P log of P squared plus Q log of Q squared. That's it. And this actually conspires to give you this constant that, well, you know, it's sitting in the constant that gives you the normalization here. Okay? Anyway, you should fix, because if you approximate the distribution function, anyway, you should fix it. So this is incorrect. Thank you for pointing it out. Now, well, plus a constant. All right, so now let us see what the distribution will look like. P of n is going to look like the constant that will come from normalization and this constant term here, times e to the minus n x minus p minus q squared divided by 8 times p plus q. And this is equal to a constant times exponential of minus x minus n p minus q squared divided by 8 times n p times q. All right, and therefore we see that we practically get the same Gaussian distribution as the one. With this technique, we get the same Gaussian distribution as the one we got before, right? And everything is fine. You agree? Good. All right, so we're done with probability theory. Let me now tell you something. So we have to start with, we don't have many minutes. So I'll just start with generalities about thermodynamics and various things connected to that. So what is thermodynamics? So this closes the chapter of review of probability theory. We will get back to probability theory in a few lectures. Now we pass to the second review, which is the review of thermodynamics, okay? Which we need in order to develop statistical mechanics. What is thermodynamics? Thermodynamics, well, thermodynamics is a theory that was, as I told you already, that was invented to explain and to describe the functioning of engines. That's what people were interested in. And the state of macroscopic states of matter. So, for example, understanding the concept of what is the state of a gas, and so on and so forth. Now, a gas can be, you know, if you think about a gas can be in many possible states, right? For example, the air in this room, I cannot see it, but it's probably in a turbulent state because we are, you know, we are breathing, we are, let's say, dissipating heat etc., the hair around our bodies is probably moving. But it's very complicated to describe a state of some substance in a general non-equilibrium situation, like the one up here in this room. So what, okay, apologies, I left that. So what people who were developing thermodynamics in those days decided to do is to use a very important situation for state, which is to consider states of matter in thermal equilibrium, called thermodynamic states of thermal equilibrium. Thermal equilibrium means it's a stationary state, which is not changing in time. All right. So the macroscopic variables of this state of matter, when you are in thermal equilibrium, are constants. Now, in order to define thermal equilibrium, you have to agree on what you're measuring, what characterizes the macroscopic state of your system. And you, as you know, you can characterize the macroscopic state of a gas, for example, by measuring its energy, by knowing in which volume you put the gas, by knowing how many particles or what is the density of your gas, by knowing what is the mass, the total mass of the gas, and so on and so forth. In general, or you can use other variables such as the pressure of the gas, the temperature of the gas, the chemical potential, and so on. Among all these variables, you make a broad distinction between those whose value depends on how big is the volume or how many particles you put in the system. Those are called extensive variables or additive variables. For example, the magnetization, as I explained on Wednesday. And there are also some other types of variables, which are intensive variables, pressure, temperature, chemical potential, and so on and so forth, that describe the state of your system. Now, suppose that I give you in the multidimensional space of all thermodynamic variables, given a substance, okay, I apologize that the thing is continuously disappearing. Given a substance such as, for example, air or vapor, water vapor, whatever, you want to know what are among all possible states in your phase space, in the space defined by all thermodynamic variables. You want to know what are the states that correspond to thermal equilibrium, right? Which is a subset of all possible states. Well, in order to figure out what are the states that correspond to thermal equilibrium, you have to describe the hypersurface in this multidimensional space that describes equilibrium state, which is defined by what is known as the equation of state. The equation of state is an equation that connects the various thermodynamic variables in all possible equilibrium states. And for example, you have seen this equation of state in your life and you know it by heart and probably feel it, which is the equation of state of the ideal gas that tells you that the product of pressure times volume is equal to the number of particles times the Boltzmann constant times the temperature, where the Boltzmann constant has this value here. But this is certainly not the only equation of state possible. There are others, right? For example, the van der Waals equation of state, the equation of state for a magnet, and so on and so forth, right? So don't think that ideal gases are the only substance that exists in this world. Now, since we will be using ideal gases a lot, let's agree on something. The equation of state for the ideal gas is frequently written as P times P and 3 Boltzmann times T. Now, you can define a new constant, which is the Avogadro number times the Boltzmann constant, which is given by this 8.31 joule per mole per Kelvin. This is called the gas constant, R. And if you write it up in terms of R, then your equation of state becomes P times V equal to N, little n, which is not the number of particles, but the number of moles. 1 mole is an Avogadro number of molecules, times R times T. So this is the way chemists write down this equation, okay? Because they like to use moles. Now, what happens if instead, you know what is an ideal gas? I mean, have you ever seen an ideal gas in life? I mean, you know, you heard the story of the ideal gas, but where is the ideal gas? I mean, how comes that they invented, they measured this equation of state? Where do you observe an ideal gas? In which limit of a gas the gas behaves as an ideal gas?
Very high temperature.
Think about it. What is an ideal gas? Okay, you don't know. I mean, you're not supposed to know what is an ideal gas, right? Because you're taking a class in statistical mechanics. But all of you already took a class in statistical mechanics, so you already know more or less what is an ideal gas. An ideal gas, when you do statistical mechanics, is a gas of non-interacting particles, right? So when particles are practically non-interacting in life, when, you know, if I put 2 particles in this room and the room is empty, are they interacting? Because with, you know, the probability to find each other, you know, it's so small. Practically, they never find each other. So the same story is the same story for the ideal gas. Essentially, if you have a gas at very low densities, it looks like an ideal gas, right? So in practice, this equation of state is the equation of state that is supposed to describe gases at low density, sufficiently low densities, where the distance between molecules is so large as compared to the typical radius of their interaction that in practice they never interact. They are like free particles, thermally agitated free particles. Now, what happens is that ideal gases are just a limit of real gases. Real gases have molecules that do see each other, do collide, do interact, etc., etc., etc. And therefore, already the guys doing thermodynamics in the past asked themselves, how do I correct the equation of state in order to get something that describes real gases and not ideal gases? Well, one possibility is to use the so-called van der Waals equation, which we will derive by statistical mechanics. It's going to be the most complicated calculation that we will do in this course, the derivation of this equation of state. And is essentially telling you that, you see, to the pressure and to the volume, you add 2 terms that describe the effect of interaction. This term here, for example, describes the fact that close to a molecule, if you have interaction, you have so-called excluded volume. 2 particles cannot go closer than a certain radius. And this radius is proportional to this constant. The volume, this excluded volume, gives you this constant B. You have to take it out from the calculation of the volume, and that's one correction. The other one comes from long range, from a correction to the pressure coming from the long range periods of interactions. Anyway, you see that the structure of the equation of state is the same as the ideal gas equation of state, but you have to correct, to change the pressure and the volume to account for interaction. This is the basic idea of the van der Waals equation of state. Well, this is another equation of state, which is the Curie equation. It just tells you how to compute the state of a magnet. So it's another example. Now, next time we will be discussing the first law of thermodynamics, the second law of thermodynamics, and so on and so forth. But let us start with the zero law of thermodynamics, which is very, very simple, but very non-trivial to some extent. If A is in thermal equilibrium with B, and B is in thermal equilibrium with C, then A is in thermal equilibrium with C. Okay? So in other words, if I put my hand on this table, no, well, that's too complicated. If I put a spoon in boiling water, and then I put the spoon close to something else, they, after some time they will have more or less the same temperature. Or if you take three liquids and put them in contact, they will reach a state of thermal equilibrium in which they share the same temperature, and so on and so forth. All right. Actually, we will calculate what is the condition for thermal equilibrium, for example, in that. And we will see that the condition is essentially the derivative of the entropy with respect to the energy of the three objects is equal, and the derivative of the entropy with respect to the energy is the inverse temperature. So thermal equilibrium between two objects is just related to the fact that they have to have the same temperature. As you know very well nowadays, when you try the temperature with the thermometer. Well, now you do it with the thermal scanner, but it's not as good as a real standard thermometer. All right. So all of this is just the beginning of thermodynamics. So on Wednesday we will start with the first law of thermodynamics and consequences. And for today we're done. So are there questions? Talking for an hour and a half with a face mask on is not very easy. I mean, it's not extremely easy. No questions? Okay. If no questions, next speaker. So I'll see you on Wednesday. Bye-bye, guys. Bye. And also this time I didn't record. I forgot. It was pretty good. Yeah, the ICTP is recording. Anyway, it's not important to record the, with the camera because I'm not using the. But